Okay, right. In this lecture, we'll cover graphs of exponential curve and logarithmic curve. First thing, exponential curve. Suppose my function is f of x equals a raised power x, where a is positive and a not equals 1. Because if a equals 1, we'll be getting a constant function. What if a is negative? Suppose y equals minus 2 raised power x. If x equals 1, then y equals minus 2. If x equals 2, y x 1 y minus 2. If x 2, y equals plus 4. What if x is half? What if x is 1 by 4? We'll be getting complex values. So we can draw this graph if a is greater than 0 and a not equals 1. And there are two graphs. First, this graph is when a is greater than 1, and this graph if a lies between 0 to 1. There is nothing much to talk about it, just pictures and whatever we can learn out of it. So this is my graph if a is greater than 1. This passes through 0 comma 1, cuts y-axis at this distance 1. Likewise, this passes through 0 comma 1. This graph does not touch x-axis. Likewise, this one. This is tending towards plus infinite for x tending towards infinite, and again towards 0 when x is tending towards minus infinite. This one is just opposite, tending towards 0 when x is tending towards infinite. This value is tending towards plus infinite when x is tending towards minus infinity. This is a strictly increasing graph, because if you increase x, you're getting increase y. If you keep on decreasing x, you will be getting smaller and smaller y's. This one is just opposite. If you increase x, you'll be getting smaller values. This behavior, y is proportional to x, output is proportional to input, and this particular graph is output is inversely proportional to input. And one more thing, both these graphs are, there does not touch x-axis, and all values are greater than 0, which means exponential curve is always positive for all real values of x. Okay, suppose a question is, we want to solve this particular equation, 2 raised power x square greater than 2 raised power x. These two values follow this particular exponential curve. If f of x equals 2 raised power x, which means this kind of graph is increasing, which means if this output is greater than this output, this input must be greater than this input. So x square greater than x, and then this inequality, using wavy curve method we can solve this equation. In equation, x lies between minus infinite to 0 and then 1 to infinite. Okay, now we are trying to move to this logarithmic function, but before that, suppose this exponential curve, I write y equals a raised power x, converting this into logarithmic function. So x equals log of y to the base a. Now for this particular exponential curve, a should be greater than 0 and a not equals 1. Okay, exponential curves are always positive, which means a raised power x is always positive, which implies y is greater than 0. So if y equals a raised power x, there are two conditions on a and one condition is on y. Not exactly condition, but rather inference from it. Which means if we transform this function into exponential curve, this x equals log of a to the base y. Right. So one thing is, this x should be this a should be greater than 0, a should not be 1, and this particular y should be greater than 0. Okay, let's move to this part. F of x equals log of x to the base a. X is input, a is base of this log. First condition on this a should be greater than 0, a should not be 1, and then this input should be positive. Suppose we want to find domain of this particular function. F of x equals log of number is 10 minus x to the base x minus 1. This x minus 1 base should be positive, So x minus 1 should be greater than 0, should not be 1. So x minus 1 should not equals 1, and then 10 minus x is greater than 0. Solving this, we get x lies between 1 to 10 except point 2. Like this particular exponential curve was increasing if a greater than 0, decreasing when a lies between 0 to 1. Likewise, we are getting two different graphs for log. This particular graph is for a greater than 1 and this is for 0 to 1. Curve passes through 1 comma 0, cuts x-axis at x equals 1. This one also cuts x-axis at x equals 1. Graph does not exist on negative side of x because of this condition. This graph is positive when number is greater than 1 and negative when number lies between 0 to 1. This one is just opposite. Number if lies between 0 to 1, log is positive, otherwise negative. This particular graph is increasing function x and y. Y is proportional to x. If you increase x, y is increasing. If you decrease x, y is decreasing. Proportional relationship. This one is just opposite to it. If you increase x, y is decreasing, is larger, negative. So this graph, y is proportional to x, increasing function, y is inversely proportional to x, which means decreasing function. Okay, so based on these two graphs, suppose we want to solve this inequation. Log of x minus 1 to the base 2 is positive. Base 2, which means this is my graph. This number, log of this should be positive, which means this number x minus 1 must lie on this side. So x minus 1 is greater than 1. Solution is 2 to infinite. Second question is, we are comparing two logs and the base are same. Left hand side is log of x square to the base half must be greater than log of 5x minus 6 to the base half. Base half means decreasing function. If this output is greater than this output, this input must be smaller than this input, provided log exists. So x square should be positive and this 5x minus 6 should be greater than 0. So overall x should be greater than 6 by 5. Solving these two, x square less than 5x minus 6, using wavy curve method, you can find the solution. X lies between 2 to 3, which satisfies this condition, 6 by 5. Okay. One slightly difficult question at this stage. We want to find solution to log of sin x to the base half greater than log of cos x to the base 2. Base is 2. Log of sin x to the base 2 greater than log of cos x to the base 2. Base is 2, which means increasing function. So if this output is greater than this output, this input sin x must be greater than that particular input. Sin x should be greater than cos x. So sin x must be greater than cos x. And then sin x must be positive, which means first quadrant or fourth quadrant. Likewise, cos x must be positive, which means first quadrant or second quadrant. So the common part is first quadrant. So ultimately, we need to solve this particular inequation in first quadrant. I have drawn sin x using a blue color and then cos x using green color. Hope you are able to differentiate these two colors. This one is sin x from 0 to pi, 0 to 1, and cos x from 1 to 0. Point of intersection is midpoint using symmetry or 10x equals 1. Point is pi by 4. Sin x must be greater than cos x, which means part of this. So solution is pi by 4 to pi by 2. That's it. And rest of the things we'll cover in next videos.